important to talk about. We have one more phenomenon to talk about, a climatological force that affects the amount of precipitation that you get in any given area on land masses. And then we're going to turn our focus and think about the movement of energy and matter through the ocean and try to understand how that drives weather patterns as well, because it's quite significant. The good thing is there's not a lot of new things to learn. Everything about convection cycle and density and gravity that we've already learned is just going to show up again in a new form. So let's get started here. This is what the learning targets look like for today. So we're going to think about one layer that we haven't put onto this yet is the understanding that there's altitude at play on the Earth. And then we'll look at ocean water circulation on the surface, and then deep water ocean movement, and then talk about the consequences of this huge climatological phenomenon called El Nino Southern Oscillation. So lots of key terminology to get, but it shouldn't be too bad. Let's do it. In this class yesterday, we started talking about this just a little bit, and I took this picture from Google Earth after our discussion because I thought it was really interesting. So the question was, well, why is it so dry in certain parts of the Earth, North America, and other parts at the same latitude are wet? And it's because we have actually a lot of variability on this globe in terms of what is the elevation profile of the Earth. So we have mountains, we have valleys, we have rolling hills, all kinds of things. And those terrestrial bodies have the capability of disrupting weather patterns. So let's check it out. I grabbed as an example a data set about the Sierra Nevada. So the Sierra Nevadas, if you don't know where those are, that's in the eastern side of California over into Nevada, and they go all the way up into almost where the California-Oregon state line connect. So it's in this area right here. You guys remember from when we went outside, where does most weather occur? At which altitude or which elevation? Yeah. 3,000 meters. About 3,000 meters, 3 kilometers. And the air molecules can move up 10,000 kilometers. They can move up to really high elevations because they're light and the energy has the capability of moving that. But the reason for a lot of weather patterns at 3,000 is because it's hard to pull heavy, wet water molecules up. So here's what it looks like. For example, we have a convection cycle trying to move air molecules in one direction, but then they get disrupted by the profile of the Earth. And so we're trying to carry it up. And if you look at this graph, this is showing the altitude in kilometers over the space horizontally across the Earth. And so here's 3,000 kilometers. It's really hard for us to take more water molecules and lift them up over the mountain and carry them to where the wind's trying to take them to go. So what we traditionally see is, as the wind blows it up, we start getting a lot of rain in this area, a lot of precipitation, because we don't have the energy to continue to carry those water molecules up. And so then the air molecules make it all on the other side, but now they're dry and cold. And so we end up with a desert in those areas. We have two terms that just help us kind of understand. And so on this side, this graphic right below it is showing the annual precipitation across that same profile. And so you see, right here, there's a lot of rain on this side of the mountain, and over here, it's extremely dry. We call that whole thing the rain-shadow effect. And the side with a lot of wind and precipitation that's trying to blow, we call that the windward side. So it's usually way more productive of an ecosystem because of the availability of moisture and precipitation in that area. And then the leeward side is what's known as in the rain shadow. It's on the dry side. So right here is the Sierra Nevadas. I didn't point this out very well, but you can see super dark. Lots of forests, very productive ecosystems because of a lot of rain. But not much of that moisture is making it over the mountain. And this is the Great American Desert in Nevada, Utah, up into Idaho. And it's because it's hard to move all the water molecules over the mountain. We call that whole thing the rain-shadow effect. In a somewhat disjointed fashion, that's it for terrestrial. That's it for the terrestrial side of climate and weather. But we're going to turn our attention and try to understand the movement of ocean water now. sorry about this formatting here where it says the ocean gyres below. I'll give you that word here in a second. But this is another graphic, and you'll notice it's a really similar graphic to what I gave you when we first looked at the air currents on the Earth, also generated from NASA over the period of about 1 week of time, just playing on loop. And you see a lot of the same patterns. It's movement, and it's circular, and in some places it's really concentrated, moving fast, and in other places it's not very concentrated, and it's moving really slow. We call the movement of this ocean water these ocean gyres. Here's the picture from the textbook. And we're going to try to break this down here in a second and understand. I don't need you to memorize all the names of the ocean gyres on the Earth, okay? So in your study, don't waste your time trying to memorize that. We're going to think about this broadly and conceptually, and there's a couple patterns that really matter. So the movement of this water is called an ocean gyre. They're large-scale water in circulation, and they're driven by the winds. What's the best soup? Who likes soup here? Anybody? Oh, Santi, what do you like for soup?
Chicken noodle soup.
Yes. That's what I got in my last class. I got a lot of fans of chicken noodle. Nobody's ever had minestrone?
Broccoli cheddar.
It's not that good.
Get out of here.
Right now.
Get out of the class. Minestrone is good. It's the best for this example, but chicken noodle soup is okay as well. We'll use it. It'll be all right. So look at that thing that I just pulled up there, that statement. It says that the ocean gyres are driven by the winds. And the winds are always going, which way do they go?
High to low.
High to low. And what are we talking about when you say high to low?
Pressure.
It's pressure, right? So what we see is the winds are blowing across the surface of the ocean in the same way that you would blow on a bowl of hot soup. If you blow on hot soup, what does it look like? Tell me what you see. Is the whole soup getting stirred up?
No, it makes like ripples.
Makes some ripples, and where are the ripples? On the top, in the middle. They're on the surface, right? If you blew your soup so hard that you were stirring up the bottom of your chicken noodle soup, you got soup all over your face, my friend. It's too hard. If you blow, you're blowing on the surface, and it's blowing the top part, the surface part of the soup from one side, from the side closest to your mouth, to the other. The source of pressure is your mouth, and you're blowing away until it hits the other side of the bowl, and then that's where you start to see some mixing of the soup underneath, right? Because that soup that you blew over to the other side of the bowl has nowhere to grow. It hit the boundary. So I'll come back to this northern hemisphere and southern hemisphere thing in a second. It's only blowing the top part of the ocean, and that's important because we have to understand there are other processes that move the lower parts of the ocean. But ocean gyres is only the top part. So let me get to this piece here. So we have on the surface of the Earth, if we look at this, we have the Hadley cell at the equator to 30 degrees, and it's going up. And then we're coming down, and we're trying to go from high to low pressure here. But in the southern hemisphere, we turn to the left, or we turn counterclockwise from your vantage point from above. And in the northern hemisphere, we're trying to go towards the equator, and we're turning to the right. And so we see circular patterns. Why circular patterns? Because it's the wind that's blowing it, and the wind moves in circular patterns, right? So in any place where the wind is blowing the surface water up against the boundary of a continent, that's where your soup starts to get stirred up. The reason that that matters here, we don't talk about this a lot now, but we will talk about it a little bit more, is these places. So here, it's blowing up against South America, here against the Central America, here over by Africa, the northern part of Africa. This is where we get this phenomenon called upwelling. We're stirring up the nutrients from lower in the ocean where all the dead things decay and float down, and that makes these very productive ecosystems, very productive marine ecosystems. This is some of the most important places in the world for ecosystem productivity, and it's because of that upwelling from the ocean gyres, right? And you'll notice we have some diverging currents, things are moving, but it always fits with what you would expect to find due to the convection cycles, Hadley, Ferrell, polar cells. Yes?
So this is kind of more the Coriolis effect, but you were talking about it a little bit. So you said you go clockwise in the north.
Yeah.
How come when you have like a hurricane, it looks like it's going counterclockwise?
Because the pressure is going from the outside part to the in, so that you have to remember it's always going to the right in the northern hemisphere. It's looking clockwise, but it's wherever the high pressure area is towards the low pressure. So in the hurricane, the center is the low pressure area where everything's flowing into, not the outside. And that's why it looks like it's going the opposite way. You don't have to know that. It's just like a cool thing. That's cool. But always high to low, okay? Does that make sense? But in the southern hemisphere, they do spin the opposite way because of the Coriolis.
I was looking at that and I found a cool video. They have a little tub and they put it on the equator and you can see the water drain perfectly normal, and then they go like 20 feet to the south and 20 feet to the north, and it spins in opposite directions on each side.
I've seen that video. That's awesome. If I find it, I'll send it out. It's pretty cool. That's a pretty cool thing. Does this make sense about ocean gyres? Okay, good. We're going to layer a little more complexity. We're going to move from ocean gyres. I'm going to skip past this because we were able to do it yesterday. We had a great period yesterday. We got a lot done. And now we're going to talk about this phenomenon called thermohaline circulation. I'm going to show this video because I think it has a lot of really good animations in it, and I think they break it down in a good way. And we'll pause and go back at a couple spots. But we're going to look at all of these things as we watch the video. So there's 7 questions. How does it get the title and why do we call it that? What's the role of density and gravity for ocean water and why does it matter? Well, it matters for a specific reason. It does some key things in terrestrial climates as well. And then we're going to look at the characterization of the movement of water and then how human impact is changing it a little bit. The video is about 4 minutes long, but we'll spend a little more than 4 minutes on this whole thing here.
The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system.
Okay, this is the first part to pause, and this is a really important piece. The thermohaline circulation is the movement of water across all of the oceans. It exchanges movement, so that's how you end up with water from the Indian Ocean and the Atlantic Ocean, and then the Atlantic to the Pacific, and so on and so forth. And it's because of this. The ocean gyres is only moving the surface water, and it's kind of staying in those same patterns because the circle just goes round and round and round. So this is already distinct because it's responsible for exchange of water from one place in the world to another place.
The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. With thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins.
Okay, so let's just talk about a couple things and we'll keep going here. So the first thing is we're moving water across the ocean in the first stages because of the wind. And hot water tends to evaporate. And so if we say, if you know the conventional way of understanding concentration is the amount of solvent over solute. If you're taking out water, you have more salt at a higher concentration, and it tells you more salt is more dense. You're putting a solid in a liquid, so of course it's more dense and compact. That's going to make it heavier and more likely to fall. So part of the thermohaline circulation is the temperature, and part of it is that if you have saltier water because of evaporation occurring, it's also heavier water. Okay? Everybody's got that?
The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius.
So what you're seeing here is this is the North Atlantic Ocean gyre. Surface water is blowing from around the equator over here in Africa, where it's pretty hot, into the Gulf of Mexico, where the water is shallow, so it gets even hotter. And the reason it moves out from here is going to be 2 reasons. One is just the ocean gyre is going to continue to blow it in this direction towards Europe in a clockwise fashion because we're in the northern hemisphere. But the next is this piece around salt, which they'll explain.
The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current, and a third part flows north, where it releases a lot of heat into the atmosphere as the North Atlantic Current. The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, the so-called chimneys, roughly 15-kilometer wide pillars with water falling up to 4,000 meters. 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world.
So this piece is key. So the dense cold water is falling really fast. That's creating a vacuum, which is pulling the hot water from the Gulf of Mexico over even faster. But the amount of water is huge. That density is not insignificant. It's 15 times more than all the rivers combined. It's a colossal amount of water. You don't have to know that number, but it's a huge amount of water, right? And it's all plunging towards the bottom. This is what's responsible for the movement. It said it went down 4,000 meters, which is significantly deeper than the 150 meters of ocean exchange in the ocean gyres alone. All right?
This creates a strong maelstrom which constantly pulls in new water and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to reduce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic Current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop. What if the state covered your cost of living? Would you still go to work? Go back to school?
How do I stop it?
Not work at all?
Why?
What would you do?
Where are you?
This concept is called Universal Basic Income,
Oh,
or
goodness.
UBI, and it's nothing less than the most ambitious social policy of our time.
Die. Okay, good. We got it. All right. So you can see that amount of heat that it brings over to Europe is so significant. You take 1 million nuclear power plants to provide that same amount of heat to the region. Of course, that matters for ecosystems. but it also matters for the productivity and the human history. There's a cultural and social context, right? This place, if you know anything about history in the last 2,000 years, you know European culture has been fairly significant. Well, none of those advancements and none of that exists if this is a really uninhabitable place. So there's always cultural and social context to everything we're talking about, and in this case, the thermohaline circulation providing heat to Europe. That's a key climate driver. I want to just move forward. Does everybody feel like they understand the movement of the water and the influence of water? Good. I don't want you to memorize the complete flow here, but it's density and gravity. It's convection cycle. It's what we've been talking about a lot, and it's really important for Europe. But that other thing, and the movement of water, that exchange, this is so much strength here. This is what drives it all the way, and just let that soak in for a second. At stage 2, the plunging of that waterfall is responsible for everything between here and movement all down to the bottom. So from one pole to the other, across our Antarctic region, and all the way up next to Alaska, just from that maelstrom of salt and salty water. It's incredible, and that movement is important if we're going to exchange ocean water across our planet, which is important for ecosystems and other environmental processes. Last thing for the day. Last thing, we're going to talk about El Nino Southern Oscillation, and we'll abbreviate that as ENSO. You'll see us sometimes abbreviated as ENSO because it's not just the El Nino side, which maybe you've heard some about that, but there are actually 3 distinct phases. El Nino and La Nina, they're opposite phases of the same phenomena, and they have dramatically different impacts depending on which one you have at what time. So we're going to study this a little bit. I really like this video that I'm going to show here in a second because it's from the Australian Meteorological Society, and Australia is influenced by this pattern in all kinds of ways that are different than North America because of where it sits geographically. So we're going to watch this video and pause and think about a couple things, and then we're going to look at the impacts in one last formative exercise to end the day.
Australia's highly variable climate is influenced by the broad patterns in the oceans around it and the atmosphere above it. Some of these patterns are not only more obvious than others, but also predictable. We call these our climate drivers. One of our strongest climate drivers is the El Nino Southern Oscillation, or ENSO. ENSO is a natural cycle in Pacific Ocean temperatures, winds, and cloud. This influences climate right around the globe. In Australia, ENSO is often behind our climate extremes, from devastating floods to searing droughts. ENSO naturally swings between 3 key phases: La Nina, neutral, and El Nino. A typical ENSO phase starts in the first half of the year and lasts until the following autumn. Sometimes we can get the same phase for 2 or more years in a row. On average, it takes about 4 years to swing from El Nino to La Nina and back again. So what are these ENSO phases, and how do they impact Australia's climate? Well, during the neutral phase, steady trade winds blow across the tropical Pacific from the east to west. These winds pile up warm water in the western Pacific. In contrast, water temperatures to the east are lower as the trade winds cause cool water to be drawn up from the deep. The temperature difference across the tropical Pacific Ocean causes air to rise to Australia's north and descend near South America. This creates a huge connected cycle called the Walker circulation.
You don't need to know the term Walker circulation, but I want to pause here. So this is the neutral phase. This is the normal phase, and it says in the early stages that it takes about 4 to 7 years, and it repeats, and it's somewhat predictable, but it's not perfectly predictable. Well, let's just take the globe here for a second. Here's the equator. So we have the Hadley cell swinging and bringing molecules up towards the atmosphere, and we have a low pressure area, and we move to high pressure, and it moves over, and then cold particles plunge back towards the Earth, and we end up with high pressure here, and they're sweeping back towards the equator from high to low. And then you'll notice, as we're in the southern hemisphere, they're going to go from the high to the low and go counterclockwise or to the left, so they're pushing. And then the North American ones are going to converge in the opposite way. So we have both Hadley cells, which are the most powerful, doing the same thing and pushing water across the Pacific Ocean. And so this is what that looks like. Well, it's going to move. It's an ocean gyre, where it's the air movement blowing the water, and you're blowing hot water that's on the equator, but you're concentrating it over here on the Australian, Southeast Asian side, right? And so that's showing a profile here, and it's much cooler because we've moved all this cool, warm water over here on the South American side and the Central American side. That's what we call the normal or the neutral state.
This creates a huge connected cycle called Walker circulation. We consider neutral to be the normal phase because we're in this state more than half of the time. While a neutral phase may bring more normal weather to Australia, droughts and floods are certainly still possible. When we move into a La Nina, it's a bit like the neutral phase has gone into overdrive. The trade winds blow harder, expanding the warm pool on the Australian side of the tropical Pacific and cooling the oceans towards South America. This increases the east to west temperature difference and makes the Walker circulation even stronger, and the trade winds blow even harder again. This is called a feedback loop, and once it starts, we're locked into a La Nina until at least the following autumn. With the higher ocean temperatures, we get greater evaporation, more cloud, and more rain in the Western Pacific. For Australia, this means a higher risk of widespread flooding, lower daytime temperatures, and more tropical cyclones.
So they show all these severe weather impacts, but just to break it down, the La Nina is like the normal. It's the same thing, but it's stronger. So you're blowing on your soup normally, and now you're blowing really hard. So you're pushing it even further over this land mass in Australia and Southeast Asia. But then they show all these effects: tropical cyclones, typhoons, lots of flooding and that sort of thing. Help me make the connection between why that would happen just from moving the hot water from one place to another place. Why would we end up with floods and increased severity and frequency of storms if we...
Hot water is easier to evaporate.
Yeah. Hot water is easier to evaporate. What is heat again?
It's moving more.
It's moving. We can do all kinds of work. What kind of work do we do with heat? Usually it's lifting water molecules, right?
Yeah.
And so we see a lot of increased weather patterns in these areas. That is the La Nina side. One left to go.
The other end of the scale, we have El Nino, which is almost the direct opposite of La Nina. During El Nino, the trade winds actually weaken or reverse, allowing warmer waters to drift back towards the east. The change in the ocean temperature patterns mean the Walker circulation breaks down, resulting in even weaker trade winds and even more warming in the east. Once this feedback starts, El Nino has set in. With the warm water shifting east, the evaporation, cloud, and rain follows, shifting away from Australia. That means a greater risk of drought for northern and eastern Australia, higher temperatures and more heat waves, clearer nights and a longer frost season, and fewer tropical cyclones. While there are scientific definitions for El Nino and La Nina, in reality, no two events and no two sets of impacts are exactly the same. We also know some impacts will emerge as an ENSO event is developing, and some will persist even if an El Nino or La Nina never fully forms. The Bureau updates...
Okay, cool. So in the El Nino situation, now we're blowing on our soup, if this is normal, and La Nina's, now it's like, or potentially this way, if it feeds into itself too much, yeah.
So why does the warm water shift the other way?
Because if it shifts or it doesn't move because the winds are too weak to move it, which is usually how we see it. Very rarely do the trade winds reverse, but if they do, now you've got the same effect, but we're blowing it over by South America and Central America, which is going to bring all of those weather patterns over here, and cooler and drier and drought in Australia and Southeast Asia. So those are the couple phases there. Okay? I'm going to do a little formative exercise, and I want to explain this a little bit here in a second. But the graphic there is showing a time lapse. This is when El Nino became known to a lot of people in the world, was in the 1995, 1997 period of time where we actually did have the trade winds reverse, and we had crazy weather in North America like we hadn't seen ever. And people, oh my gosh, the winter of '97, and in Australia was really dry. So we've got this formative exercise, and what I really like about this exercise is I'm asking you to do the thing that I ask you to do a lot on assessments. Here's some information, and I want you to process and understand the information and then re-represent it in a different format. So in this case,